In a groundbreaking finding, astronomers have finally discovered the gravitational wave background, the big hum of the cosmos. This discovery shows us that the universe is constantly humming with a frequency of a billionth of a hertz. The gravitational wave background could result from colliding supermassive black holes that were earlier thought to be an impossible phenomenon due to the final parsec problem. These gravitational waves stretch light years across and have frequencies in the range of nanohertz, showing how challenging it is to detect them. Just like the discovery of the cosmic microwave background almost 60 years ago, this discovery has opened doors to new physics. So, what exactly is the gravitational wave background? Why did astronomers think that supermassive black holes could not merge to produce this hum? Finally, and most importantly, how is it going to revolutionize our understanding of the cosmos? At the core of almost every galaxy resides a supermassive black hole, which co-evolves with its host galaxy. These black holes are incredibly massive, ranging from hundreds of thousands to billions of times the mass of our Sun. A galaxy and its supermassive black hole grow under the influence of each other. Initially, astronomers believed that galaxies were isolated structures that did not interact with each other. But as astronomers built more powerful telescopes, they started observing galaxies that were not only simply interacting but also merging with each other. With this observation, they naturally became curious about the fate of the black holes at the hearts of these merging galaxies. What happens to these black holes when their host galaxies come together? Do they merge as well? The most straightforward explanation for the fate of supermassive black holes during galaxy mergers is their eventual merger into a single black hole. This occurs when two supermassive black holes come close to each other and enter a tight orbit. As they continue to approach one another due to the gravitational interactions, they release gravitational waves, which dissipate their orbital energy. This causes their orbits to gradually shrink, bringing them closer together. However, the math doesn't allow that. There is a challenge known as the final parsec problem in astrophysics. According to this problem, their orbits cannot become smaller than 1 parsec or approximately 3 light years. At such close separations, the black holes would have expelled all surrounding stars, leaving them with no means to exchange energy. Consequently, there is no other astrophysical process that can further reduce the separation between the supermassive black holes. As a result, supermassive black holes are believed to remain in close proximity without merging for significant periods of time. Now, you must be thinking that LIGO recently detected gravitational waves from black hole mergers. So why didn't the final parsec problem come into the picture in that case? Well, the gravitational waves detected by LIGO were from merging stellar mass black holes that result from the death of massive stars. These black holes are small, having masses ranging from 5 to a few tens of solar masses. But the story is different in the case of supermassive black holes. When supermassive black holes reach a separation distance of 1 parsec, it becomes difficult for them to lose their orbital energy. However, if a mechanism exists that can help them overcome this difficulty and bring them closer than 1 parsec, these supermassive black hole binaries would spiral around each other, emitting gravitational waves in the nanohertz frequency range. Given the common occurrence of galaxy mergers, it is expected that there are numerous such spiraling binaries of supermassive black holes. Detecting gravitational waves with nanohertz frequencies is quite difficult. The accuracy required for such detections was not achievable with existing telescopes. So astronomers found a solution by utilizing pulsars, which are dead stars, as messengers of gravitational waves. And the way it was done is going to blow your mind. Pulsars are remarkable celestial objects. They are highly magnetized pulsating neutron stars that emit beams of energetic particles along their magnetic axes. This results in regular pulses of emission when the magnetic axis aligns with our line of sight. The pulses emitted by these cosmic lighthouses fall in the radio frequency range and can be detected by sensitive radio telescopes. Pulsars rotate rapidly, with spin rates ranging from a few to 1,000 times per second, making their periods incredibly precise. The period of these radio pulses is so accurate that astronomers use them as cosmic clocks for precise timing measurements. They barely miss a beat. Gravitational waves, on the other hand, are ripples in spacetime, akin to ripples spreading on the surface of a still pond after a stone is dropped. Subscribe Arrowway for more such content.